Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 9 on congruence and rigid motions. So throughout this unit, we've been talking about rigid motions, specifically transformations that don't change the size or the shape of a figure. So today we're going to really formally connect the ideas of congruent geometric figures and rigid motions. So let's get into it right away. Now, rigid motion properties, these are critical to understand. Rigid motions form the basis of our understanding of congruent figures, i.e. two figures that look identical, but they could be in a different location or a different orientation or something like that. That's because of the important properties of all rigid motions. So let's bring this up to the top so we can really talk about these properties. Here we go. Number one. Rigid motions map lines to lines, segments to segments, and rays to rays, meaning that they don't change a line into a segment, they don't change a segment into a ray, they don't change a segment into a circle, right? If something starts as a segment, after you use a rigid motion on it, it ends as a segment. And again, that's not true of all transformations. I could come up with a transformation right now that would take a line segment and it would change it into a circle. You don't want me to go there, but I could do it. I could. Anyway, so, let's talk about the other two important properties. Number two, rigid motions preserve distances. In other words, they preserve the lengths of line segments. And finally, rigid motions preserve angle measurements. Now, those last two are really the ones that we kind of concentrate on. This idea that if I had a line segment, and I used a rigid motion to transform it or to map it, then its image line segment would have the same length as the original line segment. Likewise, if I had an angle, in a figure or just a random angle hanging out, and I transformed it with a rigid motion, then the image angle would have the same measurement as the pre-image angle. All right, that being said, let's take a look at exercise number one. In the image below, triangle DEF is the image of triangle ABC after a translation along a vector that points from point A to point D. Based on the properties of rigid motions, do the following. Letter A, name segments that are congruent to the ones listed. Mark on the diagram. All right, so just to make sure, the idea here is that there's a vector that points from point A to point D, and I took every point in triangle ABC and I mapped it using that vector, even points that aren't every single point, the idea is I mapped it using that vector. Maybe I'll just have this vector hang out down there, okay? So based on that, and on the fact that rigid motions, translations are a rigid motions preserve lengths and angles. In letter A, tell me what length or what segment must be congruent to AC, what segment must be congruent to AB, and what segment must be congruent to BC. Now, of course, it's always tempting to just be like, well, that one looks like it's the same length. But really understand this, I moved A to D and I moved C to F, so AC and DF must be the same length, They have to be, Likewise, I moved A to D and I moved B to E. Let me mark this. And therefore, AB must be congruent to DE. And finally, I moved B to E and I moved C to F, and therefore, BC must be congruent to EF. Let me mark all of these. Double dash line there and triple dash there. That's the whole mark on the diagram. All right. Now, not only do rigid motions preserve length, but they also preserve angle measure. So, letter B, name angles that are congruent to the ones listed, mark congruent angles on the diagram. Awesome. So, why don't you write down what angles are congruent to each of these three? Now, this one's a little bit trickier to do with that vector, but again, angle ACB, when it got translated to angle DFE. And that means they must be congruent. So angle ACB must be congruent to angle DEF. I'll mark that with a single arc mark. Can't get over it every time I say arc mark. All right, then CAB, right, gets translated up to FDE. And likewise, ABC, which I'm going to mark off with 3 arcs, gets translated to angle DEF. Okay? So absolutely critical. We can say all of this is true, right? Because what we say is corresponding parts of congruent triangles are congruent, right? And it's because we get that mapping. Did I map one of these wrong?
First one should be DFE.
Oh, the first one, A, C, B, D, F, E. Absolutely. Thank you, Joey. Otherwise, the first and the last one are the same, which would be weird unless it was an isosceles triangle, which it's not. Okay, DFE, thank you. Thank you for the correction. All right, so let's keep going. Defining congruence with rigid motions. All right, so now we're going to actually define what it means for 2 figures to be congruent. Let's take a look. The definition of congruence in terms of rigid motions. If one figure is the image of another from a rigid motion or sequence of rigid motions, then we say the 2 figures are congruent. In congruent figures, corresponding sides will be congruent and corresponding angles will be congruent. Okay, so let's take a look at exercise number 2. In the diagram shown, RT and QU intersect at S such that QS is congruent to US and RS is congruent to TS. Letter A, mark the congruent segments on the diagram. All right, why don't you go ahead and do that? Remember to use single slash marks and double slash marks to distinguish between the 2 sets of congruent sides. All right, let's do it. So we get QS congruent to US, and we get RS congruent to TS. Fantastic. All right, letter B. A transformation will map triangle STU onto triangle SRQ. What is it? Justify! Exclamation point. All right, so I want you to think about it. What could I do to triangle STU, a single transformation, right? It has to be a rigid motion, a single transformation that will take STU and it will map it on top of SRQ. Pause the video now and think about what that transformation might be. All right, well, I'm hoping you said one of 2 things. A 180-degree rotation about point S, or a point reflection across S. By the way, those 2 are the same thing, right? A 180 rotation about point S or a point reflection across S. Now, justify. Well, it's really simple, right? And we'll write this down in a moment, right? Since Q, S, and U are collinear, and we know they are because QU is a line segment and S is on that, right? Because these 3 points are collinear and Q and U are equidistant from S, then if I rotate 180 degrees, right, U will end up mapping onto Q, right? Likewise, for the same reason, if I rotate this triangle 180 degrees, T will end up mapping on R. Side note, last little thing, right, S will map to itself because it's the center of rotation. So let's get all of those down. So S will map to itself because it's the center. U will map to Q because QS is congruent to US. That was fun. And T will, will map to R because RS is congruent to TS. Right? Perfect, right? We can rotate this triangle 180 degrees about this point, or say we reflect it in that point, and that triangle will then map onto that triangle. Now, let me throw these things out there really quick. I just want to make sure I mark them in the same way. Come on. Okay. Letter C. Why can we now conclude that QR is congruent to UT? So why can I now conclude that this segment must be congruent to that segment? Pause the video now and see if you can write something down. Well, there's many correct answers here. One correct answer is to say, well, because we've got this rigid motion, the two triangles are congruent, and these two sides are corresponding sides of congruent triangles. You could also say that a rotation is going to preserve distance between points, and so because QR is simply the image of UT, then they must also have the same length. I'm going to go with that corresponding parts, all right? Since triangle QRT is congruent to triangle QR, not QRT, QRS, sorry. Since triangle QRS is congruent to triangle UTS, QR must be congruent to UT because they are corresponding sides. Now, we're going to use this word a lot in future lessons, and I've already used it quite a bit. And again, sometimes I use terminology so much that I get used to it and I don't think about whether or not you're used to it. Corresponding just means in the same place on the triangle, right? So in other words, like UT and QR show up in the same place on the two congruent triangles, and because they show up in the same place on the two congruent triangles, they themselves must be the same length. They must be congruent. All right, let's keep going. Now, showing that triangles are congruent. This is kind of cool, and you'll definitely be asked to do this plenty in geometry. Let's talk about it. Showing two triangles are congruent using rigid motions. To show two triangles are congruent using rigid motions, one must find a rigid motion, or a sequence of rigid motions, that maps the three vertices of the first triangle onto the three vertices of the second triangle. Awesome. So let's take a look at that in exercise number 3. In the diagram shown, segment LM is congruent to segment LP, and segment MN is congruent to segment PN. Letter A, mark the congruent segments on the diagram. Awesome. Why don't you go ahead and do that? Okay, here we go. This picture should look kind of familiar to you. LM is congruent to LP. MN is congruent to PN. All right, simple enough. All right, letter B. Draw in an auxiliary line segment from M to P. I'm going to always have a problem pronouncing that word, auxiliary. Auxiliary. Yeah, anyway. So what is that? What is that bold-faced thing? So sometimes in geometry, we need to draw in a line segment or a line that isn't already in the diagram to help us understand something that's going on. So it's, if you will, an extra line segment or line that's drawn in that will help us prove something. So I'm just drawing in segment MP. Make sure you draw it in as well. Okay, now letter C. Explain why segment LN must be the perpendicular bisector of segment MP. Okay, now we talked a lot about perpendicular bisectors in this unit. See if you can write down why LN must be the perpendicular bisector of MP. Take a moment to do that. Well, this all relies on something we saw a few lessons ago, which was that if a point like L is equidistant from the two endpoints of a segment, right? It's the same distance from P as it is from M, then it must lie on the perpendicular bisector of that line segment. Likewise, N is also equidistant from M and P, so it must lie on the perpendicular bisector. And because they both lie on the perpendicular bisector, then the line that connects those 2 points must be the perpendicular bisector. So let's get that down in words. Since points M and N lie equidistant from since points L and N lie equidistant from points M and P, they both are, you just never know when that red's going to come out. And again, they both are on the perpendicular bisector of MP. It's like that portion of my screen just wants to be read. Okay, so finally, let's take a look at letter D. What rigid motion would map triangle LMN onto triangle LPN justify? Well, I bet you can figure out what that rigid motion is, but can you justify it? Pause the video now and try to write down both what the rigid motion is and why it would have to work based on what we know so far. Oftentimes, the rigid motion is obvious and the justification is a little bit harder, right? We're talking about triangle LMN. Let me actually outline that in red. Triangle almost did it, LMN, right? Sorry about the miss there a little bit. I want to take that triangle and map it down here. Well, what would do the job? Would be a reflection across LN. So first, let's write that down. And I think we'll just stick in red. A reflection across LN. Now, how do I justify it? Well, this goes back to saying, look, whatever the rigid motion is, you now have to explain why each one of the vertices of one triangle get mapped onto the 3 vertices of the other triangle. Well, 2 of the 3 vertices are going to be a piece of cake, right? Because points L and N are going to get mapped to themselves because they lie on the line of reflection. So that's the first thing I'm going to do. Points L and N map to themselves because they lie on the line, hey there, the red didn't hurt me, of reflection. Guess that's the key. If I just stay in red, then when it turns red all of a sudden, it won't look so strange, although now it's a thicker red. Anyway, so good. 2 out of the 3 are done. The real question then becomes, why does point M get mapped to point P underneath this reflection? Well, that goes back to what a line reflection is, right? And point M must go to point P under this reflection because LN is the perpendicular bisector of MP, and that is the very definition of a line reflection. So point M maps to point P because, that's not the word because, and I'm going to draw this in right here just so that we have it, because Ln is the perpendicular bisector of MP, which is why it was so important to draw that auxiliary line in, right? Without drawing in segment MP, it would be harder to really be able to think about that perpendicular bisector nature, right, of Ln. Okay, final little piece, letter E. Based on the fact that triangle LMN is congruent to triangle LPN, explain why you can conclude that LN bisects angle MNP. Ooh, this is a good one. Pause the video now and see if you can explain, just based on this fact now, okay, why we can now say that LN bisects angle MNP. All right, well, first things first, right? Let's make sure that we understand what angle we're talking about, what angle we're bisecting, right? That's MNP, right? That's this thing. All right, let's work our way a little bit backwards, right? There's angle MNP, right? And obviously LN is that. Now, what does it mean for LN to bisect angle MNP? Well, that would mean that this angle is congruent to this angle. So then I'm going to work a little bit backwards from that. Why should those two angles now be equal or congruent if these two triangles are congruent? Well, those two angles have to be congruent because they're corresponding angles in two congruent triangles, right? There it is. So since triangle LMN is congruent to triangle LPN, we know that angle MNL is congruent to angle PNL because they correspond. So LN bisects angle MNP because, no comma there, because it creates two congruent angles. And that's it, right? A lot of what we do in geometry, interestingly enough, will be to prove that two triangles are congruent in order to prove that two parts of those triangles are congruent. And we've actually seen that a remarkable number of times so far, all right, and we're going to continue to see it. It's generally going to be under this like broad category of what's called corresponding parts of congruent triangles are congruent. All right, let's take a look at one last problem in the coordinate grid. Exercise number 4. On the coordinate grid shown, triangle CDE can be mapped to triangle FGH using a sequence of two rigid motions. Letter A, give one sequence that starts with a translation. All right, so what I want to do is I want to somehow get this triangle to map on top of that triangle using a sequence of two transformations, two rigid motions. Okay, and I'm going to need two. One is not going to get the job done here. All right, now I'm saying in letter A, I'd like to start with a translation. Okay, now if you're kind of like really heads up about this, you can tell that I'm going to have to both translate and reflect. Okay, so one thing I could do is I could translate this thing down to here, Okay? And then once I've done that, I could reflect across the x-axis. Let's do that. Where is it? Flip, up, down. That didn't quite work. Reflect across the x-axis, and that will put me right there. Okay? Now, let me kind of undo that. I gotta flip again, up, down. Come on. There we go. So now, how do I describe that, right? I want to make sure that I can reflect across the x-axis. So to do that, I've got to translate this over to here. I could actually translate it all the way down here, and then I could just reflect it over the horizontal line that passes through G. But since we're kind of like comfortable, I hope we're comfortable with reflections across the x-axis, I'm going to just translate it to a point where I can get it across the x-axis. Now, how did I have to translate it? Well, if I track point D, I'm going to go 1, 2, 3, 4, 5 to the right and down 1. So I'm going to translate 5 to the right and 1 unit down. All right. And then the second thing I'm going to do is I'm going to reflect across the x-axis. Okay. Now, whenever there's a sequence of rigid motions that map one triangle on top of another, or any geometric figure on top of another, whenever that happens, there are literally, and I kid you not, an infinite number of correct choices. An infinite number. Here we're just doing 2 of them. Okay? Let's take a look at a second one where we're going to start with a reflection, all right, and then probably follow that up by a translation. So see if you can do a reflection first and then do a translation. Play around with that. All right, well, why don't we almost kind of just reverse these? Let's do this first. 1, let's reflect across the x-axis. Whoops. And if we do that, right, if we reflect it across the x-axis, let me flip this thing up, down. Come on. Work with me. There we go. Like, come on. Right? This time it actually sort of worked. It'll end right there. Right? So I reflect that across the x-axis, and my sort of intermediate one is right there. Now, of course, once I've done that, what I want to do is take this point and slide it over so that it lands on G. Right? So we've reflected it across the x-axis, and I can just really kind of track point D, right? Point D is sitting here at 1, 3. When I reflect it across the x-axis, of course, it ends up at 1, -3. Okay? But then, in order to get that point to line up with G, I have to move it 1, 2, 3, 4, 5, 5 to the right, and 1 up. So I'm going to translate five units right and 1 unit up. By the way, it's kind of cool to look and compare these two. In the first one, I translated 5 to the right and 1 unit down and then reflected across the x-axis. In the other case, I reflected across the x-axis and then I had to move it 5 units right and 1 unit up. You know, you'd think maybe, oh, I just, flip-flop these two. It doesn't quite work that way. Let's take a look at the last piece of this question. Given either sequence, what angle must be congruent to angle CED? Explain. All right, so what angle has to be congruent to angle CED? Pause the video now, write down the angle, and then explain why that's the case. All right, well, regardless, right, if I take this angle, CED, and I reflect it and translate it, or translate it and reflect it, it ends up being this angle. That's where it ends up mapping to. So first thing I'm going to say is I'm going to say angle CED will end up being congruent to angle FHG or angle GHF. It really doesn't matter whether you say FHG or GHF. Or you could even say angle H, because we can use it in this situation. Now, why is that? Real simple, right? Because the two triangles are congruent, and I'm going to just use the symbol for congruent. Because the two triangles are congruent, corresponding angles are congruent. And that's it. And we got a red period to end it all. Excellent. All right, so let's kind of tie this all together, right? In geometry, one of the most important ideas is two objects that are congruent to each other. Those are objects that have the same size and shape, but are located in different places in the plane, right? And maybe even oriented differently, okay? So congruent objects are very, very important. And we can really define congruency in terms of rigid motions. In other words, because rigid motions, specifically rotations, reflections, and translations, do not change either distance or angle measure, right, then any geometric object that's produced from one of those rigid motions will be the same shape and size as the pre-image and therefore congruent to it. So we have this definition. We just say, hey, two objects are going to be congruent if you can find a rigid motion that will map one of those objects on top of the other object. And sometimes it's a sequence of rigid motions, as we saw in that last lesson. Now, we're going to revisit congruency and rigid motions in the next lesson, which will be the last one in Unit 2, but then we're going to use them quite a bit just at the beginning of Unit 3 to try to establish how we can tell when two triangles are congruent to one another. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.